All right, this video is for pre-calculus. It is for section 5.2, number 1, where we're actually going to practice some log applications with exponential functions. So this hopefully will be very familiar, but now you can use logs to solve problems as well. So the first one says the temperature H in degrees Fahrenheit of a cup of coffee, T hours after it's set out to cool, is given by this equation H equals 70 plus 120, 1/4 to the T. So the first thing I want you to do is label everything. So this is the temperature, H is, and it's in degrees Fahrenheit. And they're talking about in hours. So T is in hours. If I was going to make a point out of this, it would be TH. And remember, when we do solve and show graphs, T would be here in degrees Fahrenheit, and T would be here in hours. Sorry about that. And this would be the temperature in degrees Fahrenheit. Okay, so just kind of review. I always try to make a point out of it. Think, what's my input? What's my output? The other thing I also want you to look at this is that as we look at this problem, if you think of me setting out a cup of coffee, so here's my cup of coffee. It's steaming hot, and I have done this before, where I have left for work and left my coffee on the table. Do you think that when I get home that that's frozen? And I asked that to the kids in the class. They're like, oh no, it would only be the temperature of what your house would be. I said, right, it's going to be room temperature. So as I look at this, my coffee is going to be hot right here, and it's going to cool, but then it's going to kind of level off to whatever room temperature is. So the asymptote won't be the x-axis anymore. The asymptote will be whatever my room temperature is. The other thing I want you to look at is when we look at the formula we have going on here, it's a little bit different than when you've seen before, because you have a 70 added on the outside plus 120, 1/4 to the T. So you're like, I wonder if that's got something to do with, that 70 has something to do with an asymptote. And if you remember transformations, that if you add or subtract something on the outside of the function, it raises your function up. And I'm thinking that maybe the 7 degrees Fahrenheit is my room temperature. So it's going to decrease because our b here, our ab to the x, is between 0 and 1. Our growth factor is decreasing. So I think it's going to cool, and then it's going to stay. It'll be gross when I get home, but it's not going to be frozen. It's going to be 70 degrees. Okay, I wouldn't want to drink it unless it was iced coffee. So what we're going to do now is basically go through and answer these questions. And I've graphed this so that we can look at it, what we've done previously. So they want to know, what is the coffee's temperature initially? That's when time was 0. So we're going to do H of 0. And we're going to do it 70 plus 120. I'm going to write 0.25 here just for space reasons, nothing else. And when I look at that, 0.25 to the 0, or 1/4 to the 0 is 1. 120 times 1 is 120. 120 plus 70. So that's 190 degrees Fahrenheit. And then I'm going to show you how to show H of 1 is just going to be 70 plus 120, 0.25 to the first power. Then H of 2, they want us to know after 2 hours. So all I do know right now is that it should be cooling. So the temperature should be going down. So like I told you, I've graphed this. So here's my graph. And here's our coffee. It's starting here. It's the blue, and it's cooling, and then it's coming here. Okay, and it's basically looking at like its room temperature. So I'm going to go Control T and look at the table that we have here. And again, if you look at this, the reason why I'm showing you the table is because if you have to plug in numerous amounts, if you graph it, you look at your table, you're like, oh, when time was 0, it was 100 degrees Fahrenheit. And then look, after 1 hour, it's 100. After 2 hours, 77.5. And if I were to keep going, you'd see it's closer and closer and closer to 70. So it looks like the room temperature is 70. So the reason why I'm showing you this is that you can like just look at this and plug it in after you've done the work. So I've already got the 190. I saw it was 100 degrees after 1 hour and 77.5 degrees after 2 hours. Now it says, how long will it take the coffee to cool to 90 degrees? And then they want to know 75. So I'm going to bring this up. And I really did not leave myself much room. So if I really want to know if this is 90 degrees, I'm going to put it equal to 90 degrees. And my formula is 70 plus 120 0.25 to the t. Then they want to know, hey, when it's 75 degrees. So I'm going to do the same thing here. Okay, so before what I had you do was graph the left, graph the right, and see where it crosses. And as you can see on the graph I just showed you, I did do that. So let me get rid of the table. And right here it crosses, and I graph the left and the right, and then I'm going to do my intersection. So I'm going to analyze the graph, the intersection, come on over here to see how long it takes for that to happen. And I see it's 1.29 hours, it's 90 degrees. That's what I had you do when we did the exponential. But now that we're working on the exponential chapter, I should say, now that we're working on logarithmic functions, we can actually use logs to solve this. And the one thing I keep telling everybody that is, these are like going to be way easier than the log labs I've been having you do. So let's start solving this. So I'm going to subtract, do some normal math, subtract 70 from both sides. So I have 20 equals 120.25 to the t. Then I look for some more normal math, and I can see I can divide by 120. And 20 over 120 is 1/6, so I'm just simplifying it. And look at this equation. It's so easy. It's like, oh, now I just have to natural log. So if I natural log both sides, I get the natural log of 1/6 equals t natural log of 0.25. And then I'm going to divide by the natural log of 0.25. So show that to me because I'm running out of room here. T will come out to be 1.29 hours. And we already saw that by looking at the graph. Now, you're going to do the same thing for 75. So I'm going to kind of get you started here. Is you're going to subtract 70 from both sides. So I have 5 equals 120.25 to the t. Divide by 120. So I have 5 over 120. You can simplify that if you want, but not necessary. 0.25 to the t. Then I see I can natural log both sides. So I have t natural log of 0.25 equals the natural log of 5 over 120, and then divide by the natural log of 0.25. So I hope you see that this is, you doing algebra to do this. You can always check it on your calculator. And I didn't do that right now, but I mean, if you were to check that, it's going to be, t is going to be 2.29 hours. Okay, so that's pretty cool. Before I had you show me the graph the left and right. You still can do that to check. That's perfectly fine, but I expect you to know how to do the algebra. So there's my coffee one. All right. So let's look at number 2. It says this U.S. Census projects the population of the state of Washington using the function n of t equals 5.4 e to the 0.013 t, where n of t is in millions. So this is in millions of people. And it's time in years since 1995. So t equals 0 is 1995. So basically our equation is starting in 1995. Let's describe what the formula means and what is the population's continuous growth rate. So I do know that when time was 0 in 1995, the population, or your initial value, was 5.4 million people. Okay, so that's what that part means. It's E, so this also says it's continuously, because BASIC is continuously, and it's positive K, so it's growing. Move your decimal place over to 1.3% annually. So it's continuously growing. You could say per year, continuously growing, but it's growing continuously, 1.3%. Now they want to know, what is the population t equals 0? Well, we kind of answered that, 5.4 million people. Okay. How many years before the population triples? Now, there's a lot of ways to do this, but I suggest that you look at your original and say, okay, my initial value is 5.4. If I wanted to know when that tripled, if I multiplied that by 3, I would get 16.2. So basically what I want you to do is just say, okay, I started out at 5.4. I want to know when, so you're solving for t, it is tripled, or 16.2. Now, those of you that catch on quick, if I do normal math to solve for t and divide by 5.4, I get a 3. And you're like, well, no kidding, I just multiplied it by 3, so that's why that came to be a 3. And I've had people go, why do I even have to do that? Can't I just put the 3 down? I said, sure, but a lot of people who do that forget to get rid of the 5.4. So it doesn't hurt to do this. It means you understand it. Then when you see the 3, you feel like you got it. So now I'm going to natural log both sides. And again, base E, thanks for playing. So I have the natural log of 3 equals 0.013t. Divide by 0.013, so t is going to be the natural log of 3 all over 0.013. And when I do that, it's going to be 1.31%. Excuse me, I'm looking at the next question. It's going to be 84.5 years. Sorry about that. I just gave you the answer to the next one. So you can actually, I did a graph of this one, so hang on a second. Let me find the graph. Okay, so if I come here, you'll see it's graphing. And if you wanted to graph the 16.2 and see where it crossed, you'll notice here that it's at 100 and I went up to 30. So a lot of times people go, Mrs. Pond, how do you know how to graph the window to see? Well, because if you saw that with logs and you know that it's going to take 84.5 years for it to triple, I want to make sure I'm going to come over far enough so that the intersection will happen in the window. So you kind of use everything that you have at your disposal to make sure that you have a good graph. So if we want to check that, first of all, we got to graph it. So let me escape on that one. So we're going to do Control G, and I'm going to graph just 16.2. Okay, so I'm going to hit Enter. So I know right there, whoops, I didn't mean to do that at all. But so what you want to do here, I just changed that graph. So we're not going to do the intersection. But basically, if you were going to do the intersection, it would come up with the answer we came up with. I just touched that red line, and I shouldn't have. Okay, so let's come back to our problem. Now it says convert the formula n of t equals ab to the t. So you basically want to know what your annual growth is. That's what you're doing. Now, I do know that if it's growing continuously, it's like compounded interest. My annual growth rate is going to be a bit higher. Now, because this formula, the interest rate is, the rate is so low, not interest rate, but the rate is so low. So I have 5.4 e to the 0.013 t. If I want to convert it to 5.4 b to the t, if you'll notice, my b and my e to the 0.013 are in the same spot. So what I'm going to do is put them equal to each other to see what it would be if it converted to an annual percentage. So I'm going to actually put this one in my calculator. When I do, I get 1.0131. If I subtract the 1, move my decimal place, it comes out to be, it's actually 1.31% annual growth, which is a teeny bit more than the 1.3 continuous. And the reason why it's so close is because the rate is so low. It's like only 1.3%. So if this was a bigger percent, it would be a bigger gap. And the other thing I wanted to tell you, it's kind of like, remember when we did compounding between daily and continuously? Sometimes it wasn't a big difference because compounding your money daily is very close to compounding it continuously, depending on the interest rate. All right, our last one here talks about the internet. And I know the data is older, but it's kind of true. They said in 2001, the internet was linked by a global network of 147 host computers. The number of host computers has been growing approximately exponentially, and it was 1.3 million in 1992. So that's when time was zero. So at zero, okay, it was 1.3 million. So this is in 1992, and this is our time. It's in years, and this is millions of host computers, okay? So they basically want us to come up with a continuous formula here. And I already know my initial value, my A, if you will, but then it gave you another data point. It says in 2001. Well, that is 9 years later, there was 147 host computers, which is a huge jump. And this is true in that era. So I'm going to actually start throwing in what I know. And I already know that the 1.3 is my initial value because that's when we're going to have t is 0. And yes. So now what I'm going to do is actually plug these into the formula. And remember, this is t and n. So I've got 147 equals 1.3 e. And I'm going to put the 9 in, but I'm going to switch them so it's 9k, not k9. Now, this is an easy exponential function for you to solve. So I'm going to do some normal math and divide by 1.3. So I have 147 divided by 1.3 equals e to the 9k. And then I'm going to natural log both sides, and I love it. Lo and behold, thanks for playing. I have 9k equals 147 over 1.3. Divide by 9. K comes out to be 0.5253, and it's positive, which I was hoping it would be because it's growing. So my formula is n equals 1.3 e to the 0.5253 t. There's my formula. Now they want to know, what is the continuous annual percent increase? So they're looking at that. I just take it and move my decimal place. It's growing up 52.53% continuously growing. Now they want to know, what is the doubling time? Now the doubling time should be short because this is growing so fast. So if I started out with 1.3 right here, I want to know when there's 2.6. I want to know how long, so I'm solving for t, how long it takes for it to double. When I go to solve for this and divide by 1.3, there's my 2. Should make you happy. And now I'm going to natural log both sides because I want to solve for t. Thanks for playing. So I have the natural log of 2 equals 0.5253 t, and then divide by that. So t is going to equal the natural log of 2 over 0.5253, and that comes out to be 1.31 years, which is short if it's growing that fast. So I did graph this as well, and this shows you that it's growing quite fast. So if I'm asking for it to double, and I started here, you're way down here, that's why it's such a short span of time for the time to double. So I hope that this helped you practice with logs, actually using them for real world problems. And that's the end of this in-class practice.